one of the interesting characteristics of working in Clojure and being in the Clojure community is that you'll start a conversation with somebody who's learning Clojure and explaining some idea. And by the end of the conversation, they will be expressing a pain point about something that they perceive that they're going to do in Clojure. That's a pain point that they never could have even gotten to before. Right? So you have to stop and say, do you realize that we just shot past all these problems that you used to have and that we're now on to a more innovative space? And I feel like I sort of have this on a personal level that I've shot past being impressed with David to being disappointed in him. And in a totally, 2 days ago, I would have said, wow, if 48 hours from now, I would have met the Reason Schemer guys. And David's involvement in the language is a key element to having had that happen. I would have been like, wow, that's really cool. And now I'm just like, man, David, I can't believe I only met 2 out of the 3 guys. I'm really disappointed. So if you could try to up your game in terms of getting the people in the logic programming world excited about Clojure, we'd all appreciate it. Thank you.
Is it working? Yes? Is it working? No?
A little bit closer? Okay.
Hello. 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 Okay. So I'm David Nolen. I want to talk a little bit about predicate dispatch. And if you don't know what that is, you'll sort of have an idea by the end of the talk, hopefully. I sort of have a subtitle for this talk called The Incredible Benefits of Wishful Thinking. And why? So this is an email. The type is probably too small to read, but this was from January 7th, 2009, which was like 2.5 years ago, or more, almost 3 years ago, where somebody is pointing out that it would be really cool if multi-methods worked slightly different than they currently do. And Rich Hickey responds and says, this seems like a halfway step towards this thing called predicate dispatch. And I remember thinking, what is that? I've never heard of this term before. And so I'll get into what that is, but I also want to talk another. So the talk is kind of like, I heard about this thing, and now I'm thinking maybe I should investigate it. But also 1 year ago, I was here at the Clojure Conj, and I'd opened up the Reason Schemer for the very first time. And I recommend, if you guys haven't heard of it yet, I recommend picking it up. And I also read William Byrd's dissertation on mini-Cameron, which is this logic programming system. And so the benefits of wishful thinking is like, maybe these people will actually show up a year later. So I built a version of their system, and it's really fantastic to have them here. So, I implemented core logic. Some of you may have heard of it and said, what is that logic programming? That's kind of weird. It's a faithful implementation of their system. It adds a couple things. It's mostly made more idiomatic to Clojure and has lots of performance enhancements. If you're familiar with Prolog, it adds sort of knowledge-based facilities, so you can define facts and run queries on them. And those of you that were lucky enough to see their presentation yesterday, it was pretty amazing. I'm looking forward to adding some constraint logic programming enhancement to it as well. So I'm going to be moving back and forth between the notion of predicate dispatch and pattern matching. Again, you don't have to be familiar with these. We'll get into that. I got into pattern matching because I was fascinated with William Byrd's dissertation. He had a specific thing called OCaml, which is exploring this sort of topic called nominal logic programming, which is a bit too esoteric for this talk. But what was interesting is in his implementation, he had a version of pattern matching, which was sort of I didn't like. And so I was like, oh, maybe I should look into the theory of pattern matching and maybe come up with something better. So I ended up going down the rabbit hole. I came across, there's another sort of OCaml a developer named Luc Moranger who has been involved in the theory of efficient pattern matching for a good 15 years. He had this really great paper that he published in 2008 called Compiling Pattern Matching to Good Decision Trees. It's really amazing because he sort of has taken the theory of pattern matching and come up with a much simpler compilation algorithm. And it takes this notion from this notion of lazy pattern matching, and the paper is very readable. The thing that really sort of got me excited about it was not because the first time I downloaded, I tend to just download papers and just sort of peruse them and then set them to the side. This paper particularly jumped out at me because there was this amazing sort of image of what their algorithm was able to do. By sort of adopting lazy pattern matching semantics, they're able to guarantee that the decision tree to find the matching clause will be much shorter. So on the top part, you see there's many paths to a clause, and it's a little bit hard to see, but there's the fourth clause or something. And there's many ways to get there. By applying lazy pattern matching, you see there's only one path, and there's only 4 tests. Whereas in the naive decision tree, you'll have up to 6 tests to get to the match. So I had read that paper, and I was like, this seems oddly familiar to another paper, which was recommended by Rich Hickey. And here's a bit of text from there. And it says, our algorithm first reduces methods written in the general predicate dispatching model, which generalizes single dispatching, multiple dispatching, predicate classes, classifiers, and pattern matching. I was like, so this is from the Craig Chambers paper on efficient predicate dispatch. And this was sort of like, whoa. So I read about pattern matching. I read about efficient predicate dispatch. Maybe there's some way to bring these things together. So predicate dispatch. Craig Chambers, if you're not familiar with him, he worked on Self at Sun, which is a very influential language. We use the JVM. Many of the compilation techniques that the JVM uses were innovated by Craig Chambers and his team. Weimin Chen, I believe, was also on the efficient predicate dispatch paper. So you read the paper, and what's great is that it does seem to do all these amazing things. What's fascinating is a lot of the details are actually hardwired. So the way that it deals with numerics is sort of baked into the system. And so when you read the paper, you're sort of like, well, can we get away from that? Can we get away from these sort of baked-in details? The dispatching around classes and fields in classes is really great, but other types can't really belong into the system in a generic way. And then finally, it's sort of like, even if you come up with something, and it's actually not too hard to implement predicate dispatch, but really it's hard to do it well. Good enough that us as Clojure programmers would actually sort of employ this technique in our own software. And then there's all these other challenges. So I've started down the pattern matching route, and if you're at Strangelip, you find out that Rich Hickey doesn't like pattern matching. And then I was on IRC, and Sam Tobin-Hochstadt, who actually worked on the pattern matching compilation techniques in Racket, this is like on IRC, he's saying multi-methods are scary. So like this is a bit discouraging, but But then why bother? Why go if there's all these challenges? Why bother? And it really is the case that what's amazing about Clojure is not Java, right? So if you're willing to do a bit of research, the language is malleable enough for you to add these features yourself, regardless of what other people think about these features. A big inspiration for me is the Art of the Meta Object Protocol, and this was, I think, a very big step for the Lisp community in that object orientation had come along, and they said, well, let's think about that. What is interesting about objects? What's interesting about classes inheritance? And they were able to, via macros, but not only implement object orientation, but also take it the next step with generic methods, which is sort of the predecessor to what I'm talking about. So why predicate dispatch? What's wrong with multi-methods? How many people here have used multi-methods in Clojure? And how many people love multi-methods in Clojure? So it's great. It's like this thing. It's like you learn about them, and they seem really powerful. You don't need them very often, but it's one of these things when you do need them, you're really happy that they're there. So the main thing that's wrong with multi-methods is that you have this. It seems cool, but you have this thing called the dispatch FN. It creates the values which you're going to use to match particular method. The problem with this is that it seems like you've got this great system that's open, but here we have a dispatch method which returns a vector with 2 values in it, and then all methods can match that. The problem is that you can't really change the behavior of that dispatch FN in the future. So what seemed like an open system is actually not open at all, right? Whatever idea you had in your dispatch FN, all future extension is now closed to your assumptions about what that dispatch FN was returning. So the dispatch FN is hardwired. And the question is, can we do better? And that's what predicate dispatch is all about. Before I get into that, I want to talk a little bit about Craig Chambers did this really fantastic presentation called Expressiveness, Simplicity, and Users. And what's great about this is he's talking about his 20 years as a computer scientist, as a researcher, as an implementer. And he says some really fascinating things. I like to steal slides from people that are smarter than me. And so these are not my slides. These are his slides. And he says a great thing. He says, simple ideas are easier to adopt. Everybody knows this. People prefer that when somebody presents something that it's easy to grasp. And he makes this great point. Sophisticated ideas need a simple story to be impactful. And I think Clojure has done an amazing job specifically with persistent data structures. Like the theory behind persistent data structures is very sophisticated. But what's fantastic is we as Clojure users are presented a very sort of simple interface to a very sort of sophisticated idea. So the ideal is deceptively simple, right? Even if the implementation is actually quite beyond most of our ability to comprehend it, as long as it's presented us to a way that we can leverage that sophistication without thinking too much about it. So again, to reiterate that idea, sophisticated ideas still need simple interfaces. And this is where predicate dispatch is going in the second point, which is doing things dynamically instead of statically can be really liberating, right? There are specific challenges that you're not going to encounter when you do things statically. So is predicate dispatch simple, actually simple? And I think that can be sort of shifted a little bit to say, is open dispatch simple or simpler than closed dispatch? So here is, I'm not ragging on this code. This is from Clojure Walk, which is actually quite useful. But so you see it's a conned expression, and we have, are we testing it? Is it a list? Is it an instance of IMAP entry? Is it a sequence? Is it a collection? Else do something else. Now, so this is a classic, the conned form is a closed thing. It's not open to future extension. This seems pretty strange because, object orientation came along and said, this is silly. We really should have a generic method, and we can add types, and the types just need to implement those methods, right? So object orientation figured that out, but here's maybe perhaps a possible syntax for a predicate dispatch way of doing this, right? So I have this wishful thinking of maybe def m existed, right? And here we can say inner, outer for the first case, and then form when it is a list, right? And what's nice about this is we have all the behavior that we had before, but people can add new cases as they come up with new types or protocols or what have you. The only question here is that, it's, again, can we do this in a way that it's as efficient as the conned form, right? So everybody knows the conned form is just going to expand out into branch primitives. So if we're going to do this, we would prefer that it not be any more costly than doing it in the closed way. Here's an example from William Byrd's thesis. This is the unification algorithm. So in logic programming, you often want to take two tree-like data structures and attempt to make them equal. And you see the same sort of thing happening here in the dispatch. Are the two terms equal? Is one of them a variable? Is the other one a variable? Are they both lists? And are the two things equal in a different way, right? Identical equal and then a sort of deep sense of equality. And then otherwise do something else. So I ended up changing that in core logic. And you can see right here, there's no longer that dispatch. There's no longer a con statement. We simply unify the terms, right? So we're just using polymorphic dispatch. So this is allowed to make the sort of unification algorithm look a lot clearer, right? So, in core logic, we do a thing where we extend a type and we say, if that type is being unified with a different type, do something. And so this is kind of nice so that people can actually, at any point, if you have a new data structure that you want to unify with core logic, you simply have to implement a few methods. And that's great, right? It's open extension. So, if we had predicate dispatch, but maybe we could write it maybe a little bit even nicer. So we could avoid the whole protocol thing. We don't have to define a protocol and do all this extra work. We could simply start writing code, which is what we prefer to do, saying, unify, and if the first term is a var, do something. If the second thing is a var, we don't care what the first thing is, do something. If one's a var and then one's a map, and so on. And this is kind of nice, right? I don't actually have to stop. I no longer have to stop and think, do I have to create a protocol for this, right? I can just think about what's the logical thing that I'm trying to describe. So much for predicate dispatch. So I'm going to describe a roundabout way that I think maybe is a good way to implement this. So let's talk about pattern matching a bit. Pattern matching is quite cool, I think. There's a rich history of papers going back to the 80s. And there's just an amazing goldmine of ideas there about how to do this stuff efficiently. The key enhancements that predicate dispatch really adds to this is open extensions. So if you're used to pattern matching from OCaml, standard ML, Haskell, the patterns are closed. You can't really change it later. So here is, I wrote a library called CoreMatch, which is sort of starting down the predicate dispatch road. So here is a sort of classic match expression. So you're able to match, so 3 locals, x, y, and z. Somewhere they're defined outside the scope of this little piece of code we're looking at. And we can see the cases, right? We don't care. The first clause will match if we don't care what the first thing is, but y is false and z is true. In the second case, if x is false and y is true, and we don't care what the last thing is, and so on, right? So this is a sort of top-down matching based on the cases. So what happens in CoreMatch? So people may have seen me present this before, but I'm going to go ahead and explain it in a little bit more detail. So what we do is we take this code, and we basically extract what's called a pattern matrix. So you can sort of see we now have what's called occurrences, the variables at the top, and we have each row, and we have the values that we want to match with them. So what Luc Morange did that's really clever is that he says, well, we can take this matrix and we can analyze it and see what's the best way to produce the decision tree. And he does that by saying, well, once we hit a wildcards are irrelevant, basically. So once we hit something that's sort of a concrete value or a constructor, like a type or something, we want to see what's the column with the largest number of concrete constructors that we can sort of reach. And we can see here that y has the most, right? The moment you hit a wildcard beneath, you stop. So what's fascinating about his algorithm says, well, based on our knowledge, we know that y has to be tested on the most paths. Y has to be tested on at least 2. So why don't we just shift that to the front, and we'll test it first. And this is exactly what CoreMatch does. CoreMatch will take your expression, find out which things have to be tested first, and reorder the tests. And this is what produces the compressed trees. So what's also kind of neat about the way CoreMatch works is that itself, it is extensible. Anybody can actually add a new type of pattern if they want. The whole thing is designed to be extended. So what I actually do is I say, if you have a new pattern type, we're going to pass you all the rows that match. So that means things like this. So we can match sequences. So here's an expression where we're matching sequences. So we have the sequence 1, 2, 3, 4, 1, 2, and we want to capture the rest in R. 1, and we want to capture the rest in R. So what's fascinating about sequences is you have to think about how can you pull apart sequences. You really can only get the head and the tail. You really can't jump randomly into it without dealing with linear time. So what do? We analyze the matrix. And the only thing we're allowed to do, since sequences don't give us random access, we can basically extract out the front, right? And then we put the rest in a different variable. So you see that we went from x to x head and xt, x tail, right? And so what's great about this algorithm is now we can actually share tests for xh, right? We can use one test to see which clause is going to match, and that will match 1, 2, and 3. And then we can start testing the next set of sequences to see if they match. So we can also match maps. So here's a case where we're matching, if we get a map with A and the key B is 2, then do clause 1. If we have the key B and it's 3, C4, and so on. Again, we sort of look at the matrix and we get these maps. So this is what's fascinating is maps actually give us random access. We don't have to deal with pulling off the head and then getting the rest, right? So here we can actually immediately look at all values at once. And we can basically look at x, the x with the value at the key A, x, the value at key B, C, and D. And again, we can see that we need to test B first, right? Because there's the most valid constructors to look at. So here's where it gets kind of fun. So this is a talk getting into the sort of extensibility of CoreMatch. So we can add this constraint called only. And only is really easy to do. All we have to do with only is that when we test it, we simply pass in a not found, right? So those little lightning symbols are the not found value. So if we get that, we know we fail, right? We don't want to see we want to see the not found value. We don't want to see anything else in that map. So what's cool about this is that we can use heuristics, but we end up in a situation where we actually, testing the key B and testing the key C actually end up the same, and this is actually what we want. We can pick heuristics to be which ones we try first, but we want to fail fast. If A does have the wrong key, we want to eliminate it from further testing. So vectors provide similar opportunities. This one's a little bit different because you have rest patterns, so that makes things a little bit more complicated. So again, we put everything in the matrix, and we say, okay, how are we going to analyze this? So what do? We don't want to consider the rest, and so what happens is wherever there were the most number of values before the rest pattern starts, we split it, right? And we can analyze this. We can see that XL needs to be tested first. It's a left and right half. The R's, remember, so those R's are basically wildcards. We're not testing them for anything, really. So XL is more important. And what do? We actually, again, we sort of break it apart and bring it back together, and now we can analyze the pattern again, and we are able to test 3 columns to see which one's most important. And we see that this one is the one that needs to be tested first. And again, whenever we determine something needs to be tested first, we move it to the front. So this is pretty interesting. So we're able to, this is an extensible system. Anybody can add new patterns. They can choose to analyze those patterns however they wish. So the question really here is, how do we go from closed to open? So while this algorithm is fascinating, it doesn't really bias anything as far as how do we make it possible to extend new patterns after the fact. So, and going from closed to open is very similar to going static to dynamic. So if you've actually used core match, you know that what it does is it takes your pattern and then it statically creates the very deeply nested set of con statements that represent the matches. So it gets really challenging, when we talk about not hardwiring. So once we're moving to dynamic, we don't want to hardwire anything. So open extension. So pattern matching is top-down, but this is where it gets tricky if we're going to have open extension. So open extension is not top-down, right? If somebody can add a case later, it might be that case needs to be, for some reason, tested before. A good example is even implies 2. So somebody could come up with a predicate dispatch method that says, oh, I want to test if the first argument is even. And then somebody might later decide that, well, I want to test 2. Now, the problem with that is if pattern matching is top-down, 2 will be below the even test. It's unreachable. So this is like a real conundrum, and this is the kind of thing that Craig Chambers and Weimin Chen punted on. They were like, we're going to hardwire the behavior of numbers. So the question is, can we avoid that hardwiring? It was proposed. I think Rich had mentioned that he had created a little prologue, and tried this early on in Clojure, and it was cool. It was really cool, but it was pretty slow, and it was all happening at runtime. So my idea was maybe we can insert core logic, and what we can do is we can use core logic to drive the behavior of core match. So we would actually use logic to control the output that the core match compiler generates. But again, this brings up real issues about reasoning about what's going to happen. For example, if somebody adds the 2 case, we don't want to actually break anybody else's code, right? Somebody else's code might have assumptions about the fact that something won't get tested before them. So, one solution might be namespace local changes. So this might look something like this. So you would say def pred even. So what this does is this is actually, you're hooking into the logic engine. You're saying, I now have a logical predicate which can be involved in other implication statements, and you're saying, I want that predicate to map to the even function that's defined in Clojure. So now when I go def m foo, I can go x when even, and that's great. But what's nice about when I add the next case, the logic engine will kick in saying, oh, you defined a predicate called even, which points to the function even. Before we try to insert this into our matrix, does this get subsumed by a previous definition, right? The logic engine says, oh, it does. We move it up, we move it up. We're going to test 2 before we test even. So there's lots of challenges here. So core match, being closed is really simple. It actually makes things a lot less complicated to do this kind of thing. We're just generating the correct static source. Once you start supporting dynamism, like Craig Chambers said, it's really hard. I mean, there's a really fascinating challenges there. The big trick here is how do we have a performant implementation? And whatever it's going to be, I know it's not going to be simple. One problem is that, for example, one could say, well, why don't you change to a runtime graph representation? Now, that kind of stinks because what's awesome about core match is that it's really fast. I mean, it's as fast as any pattern matcher you use in any functional language. It's as fast as pattern matches in Scala, Haskell, OCaml. It's really good. But if we change to a runtime graph representation, then we lose all the advantages of the primitive branching forms. So one thing we could do in Clojure, which we could consider, is perhaps we could use lazy compilation. So what we would do there is that we would, because this works, you would define all your code, and only the first time that the predicate gets called do we actually compile the dispatch tree. And that's great. And we can do that in the JVM. There's no problem with that. But there's a real challenge in that ClojureScript, I think, is really, really great. And core match actually works right now, today, with ClojureScript. So it's really awesome. I can use core match and compile that to JavaScript. So I don't want to lose that, right? Like, there's something nice about being able to have predicate dispatch work on any host, JVM or JavaScript. So if we use lazy compilation in the JVM, what are we going to do with ClojureScript? So the really bad solution would be, every time somebody extends, we could emit the entire dispatch, and that's not great. Code size will suffer. One thing that I thought about that might be cool, and I'm bringing these points up because I'm hoping to start the conversation, so afterwards you can bug me and say, I think that's a terrible idea, or I think that's a great idea, or you have a better idea. But one thing we could do is like def type and protocols. The way they work is that if you define your methods in a group, you get exactly the performance of the host. If you decide to use extend type, it's really fast, but there's no guarantee that's going to be quite as fast as the host provides. So maybe we could do the same thing. Perhaps we group our predicate dispatch together, and we get very optimized code. And open extension says, well, that's great for expressivity, but we don't make as strong guarantees about the performance. Same thing with future extension. Perhaps we, again, optimize the case. Well, if you decide to group your future extensions, then again, those grouped extensions will be performant. And then there's bigger, deeper questions, which are like, what about redefinition? So how do we, if somebody is developing at the REPL and they redefine a method, how do we deal with that? Another thing is, how does one introspect on this stuff? One thing that's really great about multi-methods is that at any point you can get the dispatch table and see which things are going to work. How does that work in this system is an open question. So another issue is that, so extensions that force reordering, maybe it's just, we can't do anything about that. That's game over, right? In maybe ClojureScript. Again, we can maybe solve that with lazy compilation on the JVM, but maybe with ClojureScript, if you force a reordering, then we just say, we can't do anything about that, right? You want that, so we'll just re-emit the entire decision tree. A real big idea, which I think is really was why Clojure is a good place to try this stuff out, is that Clojure doesn't have inheritance, right? Clojure doesn't sort of bring that complexity into the system. And if you read the reason schemer has a really, I think, important idea about, your clauses should not overlap. And if that is true, then something like predicate dispatch works really well. Where you run into trouble is where, something actually belongs to two different possibilities, and then we need something like prefers method. Again, please bug me about other ideas, solutions, approaches. And wishful thinking is fun. Hopefully next year on this time, it won't be wishful thinking. Questions?